All right. So I'm going to talk about what happens when you add waves together, and it's pretty simple to say what happens when you add waves together because y of x of t is equal to f of x, f1 of x minus vt. So let's, for the example on the left, say plus f of x plus vt, where they're the same function. So the total y is just going to be you add these two functions together. So on the left, you have two small Gaussians or two small normal distributions which are going towards each other. They're a little bit low. They keep going towards each other, and then they add up to something that's as big as both of them in the center. And then as they go past each other, uh they just don't add together anymore because they pass each other. So basically all you have to do is say that y total equals y wave 1 plus y of wave 2, and that's going to give you the answer for what is happening. uh yeah, the answer for what is going to happen when you add two waves together. So for example, when you add two waves together like I drew here, I didn't go to a Wolfram Alpha. I didn't go to a calculator really to look at this. So I just tried to do it by hand. But if you have one wave, two sine waves, one of which has a period or a wavelength that's shorter than the other one, then when you add them together, they're going to have a resultant wave which has the same. Oh, I didn't draw draw it that well, but that's around what it looks like. So it's going to just be like this weird blob that has properties of both the waves, but you just add them together. So this is I think this is interesting, but one of the ways that you can talk about it more is if you're talking about standing waves, which is waves where let's not even make this a graph. Let's just show x. This is x in the horizontal direction, and then this is the actual y. But if you have a wave that's traveling with a positive VT, and then you have a wave that's traveling in the opposite direction with the same wavelength of negative VT, then the resultant wavelength is same wavelength and same amplitude. Then the resultant wavelength is going to be y equals a sine kx minus omega t plus a sine kx plus omega t, where I think I might have forgotten to bring this up earlier, but I did last lecture, where omega is just equal to 2 pi over period. So when you add these up, you have to use a couple of trigonometric functions that which I'm going to bring up, but sine of a plus or alpha plus or minus beta is equal to sine alpha beta uh sine alpha cosine beta plus or minus cosine alpha sine beta. So this y becomes y of x t is equal to a sine kx cosine omega t minus cosine kx sine omega t plus sine kx cosine omega t plus cosine kx sine omega t, which becomes y of x t is equal to 2a sine of kx cosine omega t, which is interesting for the reason that uh this 2a sine kx cosine omega t, this wave doesn't move back and forth. It is just some constant 2a sine kx. So it's going to be something like this. Yeah, something like this, where the amplitude changes, but the position doesn't. So it becomes, forgive me for this getting a little complicated. The amplitude changes, so it goes up and down, but it's still in the same position. So when you see a guitar string, that's what you're seeing. You're seeing a standing wave, which is what these are called. And then the last thing that I want to bring up before I just go on about this is that what leads to this sort of interference, or this interference where a wave is bound between, so uh yeah, so I'm just going to draw out a guitar string to make this simple or more obvious, but I don't think the book actually goes that much into like resonances, which is kind of interesting. But I'm just going to go as far as the book does and say that if you have wavelength where this is a period, this is a length L, and length is equal to n over 2 times the wavelength, then this wave is going to be called a harmonic. So it's going to be called, or not a harmonic, but it's going to be a wave which is bound and allowed by the sides. So when you're talking about a guitar, you have it set up so that both sides are bound down so that the both sides are bound uh and like pinned down so that the wave has to be equal to 0 at those points. So for that to be the case, the wavelength has to be some equal. So the wavelength has to be equal to 2 over n times L, because like this, you're only going to be allowed wavelengths where at the length L, the at x equals 0 and x equals L, the two wavelengths are, or the wavelengths are equal to 0. The y values are equal to 0 at that point. So you're only able to find standing waves with lambda n equals 2 over nl, which is going to give you Fn is equal to n v over 2l is equal to n times f1. So this is how guitar strings work. They only allow a certain, they the wave bounces back and forth and back and forth and creates these standing waves that I was talking about, but it only allows certain waves to do that, and that's how guitars are able to only output certain wavelengths and certain frequencies in order to get you to listen to them and to sound clean and only at these certain wavelengths and their harmonics. So yeah, that is my lecture for the week. Hope you have a good week. And I'll see you later.